Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so now we're online, and welcome back to the software engineering session. It's my great pleasure today to welcome Rustin Lino, who's a principal researcher at Microsoft Research. So he is famous for having been involved in various projects leading to successful software tools in formal verification. He got his PhD from Caltech, and he's going to talk to us today about engineering methods for ensuring program correctness, something in which he is an expert. Thank you.
All right, thank you all for coming. I'm going to tell you a little bit about just one slide on some formal methods, some techniques used for ensuring correctness in programs that are going on at Microsoft. And then through the rest of my talk, I'm going to tell you about a specific tool called Daphne that you'll see a lot of during the summit here, and I'll give you some demos of that. But first, to set the context, at Microsoft, there are several formal methods that are being used, formal program verification techniques that are being applied in software development. And one of them is the model checker SLAM, that is these days called the static driver verifier, that we heard about in Tony Hayes' talk yesterday. Another one, which is, so the model checker there has been very successful because it's used by third-party driver developers. There's also white box fuzzing being done with a tool called Sage. So Sage has also been a great success in that it's run on hundreds of machines over long periods of time. It could be days, weeks, and to find errors in crucial pieces of software. Another tool that I'm quite thrilled about is called SimDiff, which takes two programs and compares them. So for example, when you have one version of a program that you've developed, and maybe it's very large, and you add a few lines of code to it, you'd like to see what are the semantic differences. You don't want to know just what lines of code did you change, but you want to know what was the effect of those changes. So the SimDiff tool does some things like that. And the area that I'm going to talk about here today is program verification, which is the traditional deductive program verification that people envisioned in the late 60s, 70s. There were some tools built even in the 70s. But some of the things that did not happen at that point was that the CPUs and technology and specification techniques and things like that were not as well developed. We know much better how to do those things today, 30, 40 years later. And that's what I'm going to give you a taste of today using the Daphne tool. So there are a number of program verifiers out there in academia, and you can think of plotting them on two axes. So what I have here on the chart is on the y-axis. I'm showing how much of the program you're going to try to verify. So you might be interested in proving the full functional correctness of a program, or you might just want to prove some simple properties. Maybe that the program will terminate, maybe that it will not crash when you run it. So you have a choice there in how much you prove. On the x-axis, I'm showing human effort. That is, how much does a human need to spend time with the tool to get it to do useful things? And that can mean a variety of things. It could be that you have to annotate your program in some way to begin with. You have to learn what the tool does. You have to wait for it to run. And then you have to decipher the error messages to figure out what it is that you should do when you get an error message from the tool. So in the traditional setting for in program verification, the way that it's used in education, one tends to be somewhere around here. That is, students are taught to prove the full functional correctness of small pieces of code, and that's usually done by hand. That's sort of the traditional view of how these things have been used. But there are also interactive proof assistants, so mechanical ways to check that the proofs are correct. And there I mean tools like Coq, like Isabelle Hall, like ACL2, and a number of other ones. And with those, what you get is assurance that the proofs that you carry out, are really sound mathematical proofs. But it's still a lot of effort to run one of the tools. So a number of years ago, 15, 20 years ago, I was involved in 2 efforts called extended static checking that tried to use automatic decision procedures. So in other words, proving technology that you don't have to interact with directly. They're automatic procedures. But then scaling down the ambitions so that you would only try to prove simpler properties of programs. So that area we call extended static checking. And the interesting thing I find is that you can actually use those same automatic decision procedures and push things up into the upper left-hand corner. And that's where the tool Daphne is, which I'm going to show you today. There are some other tools like Daphne, but Daphne stands out in its automation and cleanliness of how you write the programs. Okay, so let me tell you about the Daphne language, because Daphne is not just a program verification tool, it's also a language that goes with that, so that you can write programs and write specifications. And as a language, you can think of Daphne more or less as C# or Java. That is, it has classes, it has it has polymorphisms, so generic classes. It does not have subclasses, so it's not a true object-oriented language, but you can still encode tricky algorithms that have to do with pointers and dynamic allocation, the way that you would write the program in C, for example. One thing that's important for this setting is that Daphne only has sequential control. There's no parallelism, there's no concurrency in Daphne. So we have other tools that deal with concurrency, but Daphne is only sequential. Now, when you want to prove a program correct, you want to have specifications of some sort. And Daphne builds those into the language. So you can write programs, you can write pre and post conditions, loop invariants, and we'll see that today. And when you do that, you also need some specification support. That is, it's not enough just that you would have the specification constructs. You need to be able to describe data, and often you use mathematical sets, mathematical sequences. Inductive data types are quite useful many times. And something that's also very nice is to have ghost constructs. So a ghost construct, like a ghost variable, is a variable that the verifier looks on just like it was any other kind of variable. But when you compile the program, it goes away. That is, it's there only for you to communicate some things to the verifier. And we'll see an example of that. Okay, so with no further ado, what I'm going to do is launch into a number of demos so that you can just see Daphne for yourselves. And so what I'm going to do is I'll write some code. I'll write a few programs, and we can look at some other ones that I've pre-prepared. And these programs are going to be small programs that I write, just to show you what the features are and how you interact with the tool. And then I'll show you some larger programs that have also been verified with Daphne. Okay, so as a first example, I'd like to write a program that's going to use several different features of Daphne that in a way that you can see could be meaningful, but the particular example perhaps is not so interesting. What I'm going to do is define a data type. So data type is just like you have in ML or in F# or in Haskell. And I'm going to define a tree. So the tree is going to either be a leaf node, or it's going to be a node consisting of a tree. And let's put an integer in here. It doesn't matter much what it is. I could also have made it generic as that, for example. Let's just put integers in here for simplicity. Okay, so that should look like a pretty familiar data type. Now, in some languages like Scala, you have both data types like these and classes, or same things in OCaml, and that's a nice combination, and you have it in Daphne as well. So now we can write a function that operates on this data type. And what I'm going to have is a function contains, which is going to take a tree and take a given integer, and it's going to say whether or not that integer is contained within the tree. Now, I'm writing a function here. So the function in Daphne is a function in the mathematical sense. That is, you can think of a Haskell function or a or function that you'd write on paper or reason about in your head. It's not a C function. So a C function is a procedure or a method, and we'll get to those in a bit. But so a function is just a mathematical function. And the way that I'm going to write this function is in the usual style of a functional programmer, which would be that you match on the argument, and you have two cases. You either have a leaf, and if it's a leaf, then the tree does not contain whatever integer it is, because a leaf does not contain anything. And if it's a node, we have a left, we have a value, and we have a right. And in that case, we have the tree contains x if x is equal to v, or if maybe the left branch contains x, or if the right branch contains x. Okay, so far what I've written looks just like what you would have written in some other language. That is, we have not seen any verification features yet. But let me now show you what happens if you change some part of a program that is going to change how the verifier would work. So Daphne automatically proves termination of your of everything that you write down. That is, it's of termination of recursion, of methods, of loops. So here what I did was I changed the contains to pass in the tree itself. So if you pass in the tree itself, there's no guarantee that this function is ever going to terminate. And Daphne tells us that it cannot prove termination. So in this case, Daphne is not sure that maybe the program terminates for some reason that we have to explain to the verifier. So therefore it says try supplying a decreases clause, which is the specification construct that you would use in the program to reason about termination. But very often you don't have to supply anything. Okay. So that's that, and you can see that just as I'm typing in the program, the verifier is running in the background. Okay, so now let's write a piece of code that's going to do something. And what it's going to do is it's going to take a given tree, and it's going to take the elements of the tree and put them into an array. And we're going to start at some index, that is, at some index into the array. So we're given some array, and we're going to start filling the array with the elements of the tree beginning at that index. Now, we're also going to have to return something, which is we may not fill the entire array. And in that case, we're going to return the first index that was unused. So just like we have in parameters in Daphne and the other languages, you can also have out parameters, and you can have any number of them. So in this case, we need one of them, and it will be an integer. Okay. So now I'm going to write the first specification that we've seen, and the specification is going to say what my intent is. What do I mean with the fill method? What is it that it's supposed to do? Well, I'd like the fill method to have the property that that for all indices that lie between start and end, it is the case that that the tree contains the element stored in the array at that index. So this is my specification of what I'd like the method to do. And we can see that we're getting these squiggly lines right away, even in the specification. We haven't written a line of real code, executable code yet. And it's complaining that the array may be null. So this is because the specifications that you write down must be well formed in some ways. If someone had passed in null as the array here, what would this specification mean? It's not clear. So Daphne ensures that it enforces that the specifications that you write down are well formed, just like it enforces that the programs that you write are well formed. So in this case, we could try some sort of if statement, but in fact the right way to do here seems to be just to have a precondition that checks, that makes sure that no one passes in null as the array. So precondition is something that the caller should live up to, and we can then assume that in the body. Well, we're still getting a complaint. And the complaint is that the index that we're given here may be out of bounds. We know that in this context, I is somewhere between start and less than end. But we have no idea what start and end are. They could be any integers. So we will add another precondition. Another precondition that says that, that start is going to be somewhere between 0 and the length of the array. So we're going to allow start to be all the way, at the end of the array, so that nothing else could fit in there. In that case, the fill method will not do anything. And we will also ensure as a post condition that end is going to be somewhere between start and the length of the array. Okay, so once I've written those things, Daphne is happy with the specification. I get no more complaints. So some of the things that you should think about as you see these demos, by the way, is how do you write programs when you write the specifications? Do you write the specifications afterwards? Do you write them as you develop the program? If you write the specs when you develop the program, it's much easier. Something else that many of you may be interested in is when you teach these sorts of things in a class, having the tool there to explain these things for you, for the students, that is to get the red squiggly lines all the time, is something that is that helps improve the cycle of turnaround. That is, you can go through many more attempts in this way. Okay, so now let's write the code for this method. So we can see immediately when I started adding the body that it starts complaining about the post conditions. Well, that's because I haven't actually written anything yet that's going to ensure this condition. So, of course, this can be any piece of code, but in this particular case, it's going to start off almost like a functional program because I'm going to match on the tree structure. That just happens to be the case in this particular program. So, if we are given a leaf, what should we do now? And I'll be happy to take your suggestions, so just shout them out here. What should we do in the case of getting a leaf? I see a hand half raised over here. So. Any ideas? Nothing. Yeah, almost nothing. We do need to do something. We do need to set the output parameter. But in fact, otherwise, we should do nothing. So let's. So there are several ways of doing that. The simplest way is just to assign to the output parameter. You can also return a value that's going to also put it into the output parameter. But let's just leave it at that. Okay. So in the other case, when we have a left, we have a value, and we have a right. What should we do then? Well, in this case, we need to do some recursion. That is, we're going to operate filling from the left branch and taking the value itself and doing the right branch. So what I'm going to do is just call the method recursively on the left tree, the same array and the same start index, because that's where we want to start filling it. And this is going to return to us where that recursive call has ended filling in the array from the left branch. So I'll have to put that into some variables. I'll just put it in the variable end, since that seems convenient. Okay, then what we're going to do is we're going to now take the element itself and stuff that into the array. That's what we're supposed to do after all. And then finally we will call the method recursively again, this time on the right branch, and I will give it one position further since we've now filled in the V. And in fact, whatever that returns is what we want to return in the end here. So that is perhaps what you might write as the program to begin with. But now you're asking yourself, is this program correct? Can I rely on that this piece of code is really correct? And Daphne thinks that it is not. It's complaining here that we're updating a variable, namely A, that is the elements of the array, and we're not allowed to, because the specification does not tell us that we're allowed to modify anything at all. So in the specifications that you write, if your methods modify something, you must say so. You're not allowed to just arbitrarily modify things in the heap. So the specification is simple to write. We just say that we modify A, which means that we're allowed to modify the elements of the array. Okay. Well, we still get some complaints about the post condition and about an index out of range. So who can tell me why are we getting an index out of range here? Yeah. Start and end might be the same. That's true, but that's it's not always the case that it could be that the left branch was just a leaf. In that case, it would be fine to have start and end be the same. Yes, indeed. The post condition, I'm glad you answered it in that way. The post condition only says that end is going to be somewhere between start and the length of the array. So it could be at the upper end. So if it's equal to the length of the array, then we're not allowed to use that as an index. So if you think about what's going on, at some point we had better check to see if we run out of space in the array. And there's no piece of code like this, and that's what we're getting the complaint about. So we'll check here to see if end is not equal to the length. Then we will update the array and then fill it from the other side. Okay? So that looks better. Now we should get rid of that complaint. But we still have another complaint, which is that the post condition does not hold on this path. Now, if you study this program carefully, you would start to build some confidence in that the program is actually correct. But the verifier does not know it. And the reason for that is that when the verifier looks at the recursive calls, all it looks at is the specifications that are given. And in this case, it turns out that the specification is too weak. So all that is known afterwards here is that the indices between start and end are ones that are contained in the array, but it says nothing about the other ones. So in particular, the verifier thinks that the recursive call may just change the other elements in the array arbitrarily. So what we need to do in this case is write another specification that talks about the other elements of the array. So I will say that for all indices up to but not including start, a sub I is unchanged, which means that it's equal to whatever it's the old value used to be. Okay, so with that additional specification, the verifier verifies that this program is correct. So now we are done with that program. Okay, so what I've given you here in this demo is giving you a flavor of some of the features of Daphne, that is both data types and arrays, imperative features. I've shown you a few specification constructs like pre and post conditions and modifies clauses, and you've seen it check both for termination and you've seen it check against our code against the specifications. So this is the sort of way that you would interact with the verifier. Okay, are there any questions about this demo before I go on to the next one? This would be a nice time to take some questions on it. Okay, let me go on to the next demo then. All right, so I'm going to show you just a very common common example in program verification, and I won't write all the code. I'll just pull in some of it. But I'd like to see, just to show you how you might do binary search, just because if you're teaching students, or if when you were learning computer science, if you learned how to prove binary search, that's a common example, you might now compare your experience with what I'm going to show you, that is how it feels to do it in the editor on the machine. So I'm going to write a pre and post condition here. I already wrote that the array should be not null. And binary search, there it's important that we're given a sorted array. So we're going to write that as a precondition. So we're going to say that for all indices I and j, if you take an I and j that are ordered in this way, then it will also be the case that a sub I lies on that side of a sub j. Okay, that's saying that the array is sorted coming in. And as the post condition, we're going to say something about what the output parameter is. In this case, r is the name of the output parameter. And it may or may not be that the key that we're looking for in the array is there. So we will follow the following protocol, that if we return a non-negative value, that signals to the caller that the value is actually there. So I use the implication operator here. And in that case, I will just simply say that r is an index into the array. And furthermore, the array at that index is equal to the key. All right? And in the other case where r lies on the other side of 0, then we want to say that there's no element in the array that is equal to the key. So I will just simply say that for all I in the entire array, it is the case that a sub I is not equal to the key. Okay, so that's how you write the spec. Now when you write the code itself, you will go through a similar process, but I just have something that I'll pull out of the oven here. So here's the code for it. And what I want to highlight in this piece of code is that to write this piece of code, what's important is that you write down the loop invariant. Unless you did it recursively, by the way, then you would just have the specification of the method. But so that you can see that there are loop invariants in the language that you can write down. And the important thing is, as you know from binary search, is that the window between the two variables, low and high, shrinks as we go along. So let me just show you, though, what happens if we're a little bit unsure about this program in what it does, or if we can change it in some way. For example, here I'm setting high to be mid. So mid is the point in the middle that we have sampled to do the comparison. Maybe we could make the program a little bit more efficient by saying that high is mid minus 1. So then we're shrinking the window a little bit more quickly. So what you might do if you developed this program without the help of a tool is that now you would sit here and think a lot about, is this really right? Is this going to function the way I hoped it to? And here we can see that there are complaints about the loop invariance. So something is wrong, and we'd either have to rethink the loop invariance or realize that this is not a good attempt. Same thing with the, if I made a change in the other direction of low, for example, maybe I thought that the code would look nicer if I changed it in this way. Then we also get a complaint. In this case, it's complaining about termination, because this program may not terminate, because mid may be set, if low and high are just 1 apart, mid could be set to the same value as what low already was, and then you make no progress. Okay, so you can see that what you can do with the program is you can interactively change your program, change the specifications, learn a bit about what does it actually mean for the program to terminate. What does a loop invariant mean? For example, is it really necessary to have all of these inequalities, or could this really be maybe less than? Is that also an okay loop invariant? And these sorts of things are things that you can ask the program verifier. You don't have to go back to your teaching assistant and ask, and then 1 week later get an answer. Okay, so just like other tools that we use, hammer home concepts like a missing semicolon. When you have a missing semicolon, the programmer gets a report, missing semicolon, we fill it in, it's no big deal. And if we could get computer science to move in that direction for verifiers, for semantic analyzers of programs, if we just write the program, it complains something is dereferencing an array outside of its bounds, we say, no big deal, I'll just fix it. The error message is right there. We haven't even compiled this program. We have not run it a single time, and we get the complaints and we can fix the errors. Okay, so I'm going to just flash by something that is a bit larger, just to show you that that you can do challenging algorithms as well. So the Shor weight algorithm is an algorithm that does a marking of a graph. It's typically used in let's say, a garbage collector. So it does a depth-first reversal of the graph, and it marks every reachable node. And it does so not by using recursion, and not by using an explicit stack that's a separate data structure, but instead it does it by reversing the pointers in the heap going down. So when you want to reason about that, that's a complicated thing. And you can do that by, with Daphne, but you have to write the loop invariant. In this case, it's a complicated algorithm, and therefore it's a complicated loop invariant. I won't show you everything here. I'm just going to scroll by first the specification of the method, which I won't really point out here either, but you can see things like the nodes, everything that is reachable from root should be marked, is what these two lines say. And this line says that if something is marked, then indeed it was reachable in the initial state. And it's very important, of course, that you restore the pointers to what they were, which is what this specification says. It says that the fields that we're modifying are restored to their original values. Okay, so here comes the code, and the loop invariant, and the loop invariant, and the loop invariant, and the loop invariant, and the loop invariant. So it's rather big, and it has lots of quantifiers everywhere. But once you figure out what that loop invariant is, which, I mean, that's not an easy thing for this particular algorithm. The verifier verifies this one in about 3 to 5 seconds. So it's a good deal there. Okay, what I'm going to do next is depart from the basic features and show you just a little taste of what you can do with classes. And I don't have time to give you large examples or go into all of the fancy things that you can do. So I'll give you just a small class, more or less just to demonstrate the concept of a class invariant to you. Okay, so what I'm going to do here is just about the simplest class I can think of, which is going to be a class that contains one counter, that is one variable, and there are methods for incrementing this variable. But just to make the implementation a little bit interesting for the demo, I'm saying that the abstract value of the class, that is how to think about it from the point of view of specification, is that the class just contains a value. And therefore I'm making that variable a ghost variable, because this is not something that's going to be there represented at runtime. This is just for the verifier and for whoever is reading the code to understand what the code does. And in the implementation, for kicks, I have two variables. I'm going to keep track of some number of ups and some number of downs. And whatever the difference between those two is what the value of the counter is. Now in this case then, I'm actually complicating the implementation for no particular reason, but it will work for the demo to show you a relationship between various variables. Okay, and then we have the usual things like a constructor. We have something that returns the value of the counter. And you can see the specification of the get value returns into an out parameter the same value as the ghost variable says. But the ghost variable is there only for specification purposes. It's not there at runtime, so we could not implement this method by simply assigning value to the output parameter. But the specification can talk about it. And you can see the implementation returns the difference between the two. And here I'm just showing you another little feature that is nice sometimes for demonstration purposes and for reasoning about certain kinds of programs and algorithms. And that is that I'm either going to increase the ups or I'm going to decrease the downs. And I can do that. It doesn't matter for correctness which one of the two I do. So maybe this is a decision I don't want to make at this point. So I just put a star there. So I say if star. So that's a non-deterministic statement. So informal methods, non-determinism is quite common when you reason about programs or you model things. And in this case, you can also put it into the program text. In the final program that you would execute, you would not tend to use such features, but I just wanted to show it to you here. Okay, so if you want to prove this program to be correct, then you need to write a class invariant. And there are various flexible ways to do that in Daphne. And here I'm using just a very simple approach, which is the approach that the student would encounter as the first sort of thing. And that is that the invariant is written as a predicate. So predicate is really just a Boolean function. It's the same thing in Daphne. And here I'm saying that the specification variable, the ghost variable value, is equal to the difference between ups and downs. And with that, it can verify this class. Quickly, I might say as well. But okay, so that's all I'm going to say about classes. But if you have a question about classes, this would be a nice time to ask. Okay, well, good. Let me continue. Okay, when you write a program, when you get really serious about verifying programs, that is, when you're past the simple introductory examples and you're really starting to prove some programs that you care about, something that tends to come up is that you need to have some mathematical properties of your program. And this often happens even if you don't think that your program is so mathematical. So in interactive theorem provers, you can prove all sorts of things about mathematics, and those things can be used as lemmas when you reason about the program. So if you reason about the program, it's much better not to use an interactive theorem prover, but to use a program verifier that is streamlined for proving programs correct, like Daphne. But then what happens when you need to prove a bit of mathematics? Well, the nice thing is that you can actually prove some mathematics and some lemmas about your programs using Daphne itself. So I'm going to just give you a little taste of that. But if you want to prove complicated mathematical things, don't use a program verifier like Daphne. Then use an interactive verifier. But if you're just proving simpler properties that for the purpose of proving your program's correct, then this is a good choice. Okay, so what I'm going to show you is the proof of the following property that in ASCII here I've tried to show you. You may know the following mathematical property, that if you sum the numbers up to n, and you take their cubes, if you take the cubes of the numbers up to n and you sum them up, you get the same thing as if you take the numbers up to m and n and sum them, and then square the result. That may be a mathematical result that you're familiar with. If not, you will see the proof of it here. Okay, so how are we going to prove this? So again, this now looks like we're straying from program verification, but I'm showing you an application of just how you can prove a mathematical lemma in Daphne. So first I write a mathematical function that is going to be the left-hand side of this equality. So it's just going to be the sum of cubes up to n. I require as a precondition that the number that we're given is at least 0. I don't want to deal with the negative numbers here. And I just define it recursively, just like the way that you would. I take n cubed and then plus the sum of cubes for the smaller one. Okay, that should look familiar. Now for the right-hand side, the expression inside the parentheses here, that denotes a triangle number. So I call the function triangle. And it's almost the same as the cubes here. I just sum up the numbers themselves. So now I want to write a theorem or a lemma about these two things. So how am I going to express that using a programming language? Well, the way that you do it in Daphne is that you write a method and you give as the postcondition of that method the property that you want to prove. So let's think about this for a moment. What the program verifier is going to verify for you is that if you start in the start state, that is, if you start in a state that satisfies the precondition, then the verifier will prove that the body of the method will terminate, and it proves that when you get to the end, the postcondition will hold. So this is almost like you go to your mathematician friend down the hall, and you give your mathematician friend the problem, and then you go away for a while. You know that your mathematician friend will terminate his process of thinking, and when he does, he will have proved the theorem for you. So that's when you come back from coffee and all is good. So this is similar here. Okay, so how are we going to prove this thing? Well, the only technique that we have available in Daphne to us is we don't have proof tactics and things like that for the most part, but instead we write code. So what I'm going to do here is I'm going to write a piece of code that is going to convince the verifier that that is indeed a theorem. So what I'm going to do? Well, if n is equal to 0, then the case is really easy, right? There's nothing to do. You just substitute the definitions of these two functions, and then you're done. You see that everything is equal to 0. So the interesting part really comes in when n is not 0. Well, if you prove this by hand, you would use what we all know as an inductive hypothesis. You would prove this by induction. How do you do that if you write a program? Well, what you do in a program instead is that you make use of recursion. So what I'm going to do is I'm going to call the theorem recursively, passing in n minus 1. So let's think about what happens here. We're dealing with a program verifier. So when the program verifier reasons about that call, it will check that the precondition holds. Well, will it? We're passing in n minus 1, and the precondition says that we must pass in a number that's at least 0. But luckily, we had checked already for 0. So this is okay. Okay, then it's also going to check that this will terminate. And in this case, that also comes down to checking that the parameter is going to decrease. I won't go into any more details of that at this point. But you need to know that the induction is well-founded, is what that comes down to. And given those two things, we are now allowed to, upon return of the method, to assume the postcondition. So now we get that postcondition, but for n minus 1. And that's exactly what an induction hypothesis is. So in this case, I was expecting another property, but let me. So you can get more complicated things in the proofs that you supply, that you would need to have more methods, more conditions. And it turns out that Daphne also performs a little bit of induction automatically for you, and that tends to happen if you write universal quantifiers that you try to prove. So I won't go into the techniques of that. But let me point out one more thing, which is that this method, which is I've just named theorem, that's something that we're not interested in executing this. We don't want to actually compute that whatever. Actually, this method doesn't change anything. It has no output parameters. It doesn't really compute anything. But we're never interested in calling it at runtime. We just want the verifier to understand what it does. So therefore, I've made it a ghost method. So having it to be a ghost method just means that the compiler will not emit any code for it, just like a ghost variable or some other ghost construct. By the way, I should have said also that all of the specifications, pre and post conditions, assertions, loop invariants, all of those things are also ghost constructs in Daphne. So when you compile the program, all of them go away because there's no reason to check them at runtime. The verifier has checked that they will hold. Okay, so what I will do now is just quickly show you a larger program that's making use of induction. And this larger program was part of one of the verification competitions that took place last year. And it was essentially to prove the correctness of Floyd's tortoise and hare algorithm. You may know this algorithm. It's given a linked list, or if you think of it mathematically, it's given a function. But it's given a linked list, and it wants to check, does this linked list ever end with null, or does it loop into a circle at some point? That is there a cycle on it? And one way to do that is to have two pointers that you march down the linked list, and you advance the front one twice the speed as the one in the back. So that's the tortoise and hare. You have something going fast and something going slow. And if the two pointers will ever meet, you have detected a cycle, and you know there's a cycle. And if they don't meet, the one will reach the end of the linked list, and there's no cycle. So that's a tricky argument that you would make for making sure that this is correct. So this file is rather large, but we can see, let me search for induction. So in the proof of this, it happens several times that you need induction. And here it's using that induction tactic automatically, the one that's built into Daphne. Here's another place, and here, and that was it. So there are several places in the method, in the file, in the proof, where you need induction, just to prove some properties of an algorithm. And that's what you see here. So Daphne does those things automatically in some cases. Okay, so let me just get back to the slides and start wrapping up here. I want to tell you something about what the technology is behind Daphne. You have seen that Daphne runs in the background in Visual Studio, for example, and it runs in the background and it seems fast and responsive. In fact, if you look very carefully, you would have seen the CPU meter and seen that most of the time that we were waiting for the verifier, we're just waiting for a little bit of idle time so that the verifier knows, oh, this is a good time to run. So it's very fast. Daphne builds on a program verification engine called Boogie, which is also developed in our group. Boogie is a language by itself, and it has a program verifier associated with it. And what you do with Daphne and similar programs is that you translate your source language into the Boogie language, much in the same way that you would translate your source language into machine language if you want to compile it. But you build up a mathematical model in the translation into Boogie. And then Boogie computes large mathematical formulas, verification conditions. Those conditions are correct if and only if the Boogie program is correct. And those formulas are passed to the automatic SMT solver Z3, which is also developed in our group, which is the best one of its kind with this kind of application. But this is the picture that is behind Daphne the way I showed it in these demos. But that's not the whole story. Daphne is part of a whole family of various tools. And here I show some of them. This is not the complete list. There are many different program verifiers and similar tools that are built on top of Boogie that also make use of Z3, and Boogie can also go to some other verifiers, but we tend to use Z3 really exclusively. And there are some Boogie-to-Boogie transforms that can infer properties about programs or can check the difference between two programs, for example. And out of the programs on top, the verifiers on top, Several of them are developed in our group, several of them are developed in the academic community in other groups. And there have been some really impressive things being done, both using these tools. For example, the Havoc tool has checked large portions of the Windows code base for certain kinds of errors. Okay, so that's the family. So all of the Daphne and Boogie and many of the other checkers on top are open source as well, and they're available. So you can use those as starting points if you want to build a verifier. Okay, so you might wonder now, who is using Daphne? So I've shown you a number of examples. So is Microsoft using Daphne, for example? Do we use it in developing products? And that's not the case. Daphne is a research prototype. It's using and experimenting new features of specifications. And what tends to happen with those features is that some of those features, like the termination checking, some of the inductive data types and the way they've been handled, and there are probably some other features on the brink of happening as well, that are flowing into the VCC verifier, which is a verifier for C programs. And that one has been used to verify some tricky pieces of code that have been developed at Microsoft. So Daphne itself is not used, but Daphne has been used to verify algorithms that are like the ones that you've seen. And it's being used in teaching. So I would encourage you that if you're in a situation where you'd like to teach about reasoning about programs, then consider using a tool. And of course, I would recommend Daphne. I think that Daphne is the simplest one of the ones to use. But do use a tool. I think it's a really good idea. It gives the students feedback much more quickly. You can run Daphne on the web in the Rise for Fun, at the Rise for Fun site, where we have a number of tools that are being produced in our group. And Daphne recently passed 100,000 different uses, that is, different programs that have been submitted, over 100,000 of them. And up from, comparing that to January, in January it was about 35,000. So this number is growing pretty quickly at this point. There have been some program verification competitions, and there was one that gave out medals. That was the VSTTE 2012 program verification competition. And in it, there were teams from all over the world competing with many different languages, many different verifiers. And 6 of those teams used Daphne. There was only one other tool, namely Coq, that was used more often than Daphne. So Daphne was used quite a bit. And there were 6 medalists awarded. So there were 2 golds, 2 silvers, 2 bronzes. And out of those 6, 2 of them were Daphne teams. And in fact, Coq, which was used in more, did not get any medal this year. One of the other medalists was using the VCC tool. So that's also built on the Boogie chain. So if you're interested in these sorts of things, or if you have students that love programming and love getting into competing with these things, do have them, check out the verification competition. It was a great 48-hour adrenaline rush, and I would recommend it to anyone. Okay, here's the Daphne on the web, which is on the Rise for Fun website that you've seen some other mentions of during this conference as well. And there's a very nice tutorial for Daphne that you can find on that website. You might wonder, where is Daphne going next? There are a number of features that I'm rolling into Daphne, and there are some other things that are being developed around the program verification. Not just doing program verification, but thinking about the program development cycle, like refinement and synthesis. Okay, so in summary, what I've shown you is a program verifier that lets you prove not just simple properties, but that can go up to full functional correctness, so that you can verify programs, and you can do that interactively. When you interact with the tool, all of the interaction that you do is at the level of a programming language. You write loop invariants, preconditions, things like that. You don't go into mechanical a theorem prover and try to issue tactics and things like that. You stay with the program. That's how you think. So you can use Daphne yourself, both in binary forms and in source form. You can teach with it. That is, use it in teaching. Have exercises that are Daphne programs or that are using the Daphne tool, and you can extend it by getting the sources. And I'm leaving you with some URLs. But if you just go to the Daphne source, to the Daphne webpage, for which we have a little postcard that we're handing out as well, you'll find all of this information as well. Let me just give one more plug. and that is for a little video blog called Verification Corner that I do, where I have a collection of videos that's growing, where I demonstrate various concepts in program verification, and those can be fun to watch, and you might also learn something. So with those things, I'll draw to a close, and I'm happy to take any questions until Judith tells me that I can't have many more. So thank you very much. Yes. Yep.
But maybe you want to put it. Yes, if you've proved your algorithm with Daphne, but you need to use it in Java or C or whatever.
Yep.
And so maybe you don't have the same primitives. So what do you do?
Right. So so the question is then, I mean, the fact that Daphne works on Daphne programs, and you have other programs that you'd like to verify. So there are a number of, you can, if you go outside the use of Daphne, there are some other verifiers as well. For example, VSTTE is a very powerful verifier for C programs that does concurrent C programs and all of the C goriness and things like that. There are also some other tools for C# and so forth, but they're not as well developed. So there are the sources are available, and you can, I mean, if you're interested in those sorts of things, maybe there's some collaboration that could happen to beef those up a little bit more. If you use just Daphne, the way that you would tend to use it in that case is you would go to Daphne, type in your program, verify it, and then you would do a very careful job of rewriting it in Java, just hoping that you don't get things wrong. But that tends to be how it is. Daphne compiles to .NET, so you can. There's some ways that you can call between Daphne and other things. You can get the C# code, for example, that Daphne can translate to C# code. But in general, Daphne is for Daphne programs. Yeah. Yeah.
On Tuesday, you showed us a nice trick for inferring programs from specifications.
Yes.
Do you think it is possible to do this more automatically, like for program synthesis?
Yes,
at least for
on Tuesday in my Daphne tutorial, I showed some sort of techniques or heuristics that you can use, that you develop the specifications first and then the programs. Those work very nicely for certain examples. I think that has inspired my work on synthesis. In fact, that you could actually write it in that way. But there's much more work to be done, and those techniques work for certain kinds of problems where they work very well. But I think that in any case, if you have specifications in your head, even if you don't have a recipe for how to develop the code directly from it, if you keep in mind the specifications when you develop the program, you'll be in a much better shape than if you just code and you don't know really what you're doing. All right. Thank you very much. Or is that all right? One more? Or we stop. Okay. Thank you very much.
Okay. Thank you.